Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 211 Classical Mechanics. It is the 15th lecture of this course, and today we'll be going through the derivation of Lagrangian equation from the D'Alembert principle. First, I will give the learning objective. At the end of this lecture, the student will understand the concept of Lagrangian mechanics. In this course, we are following the book Classical Mechanics by Goldstein, Paul and Sufco, 3rd edition. In this lecture, I have taken some of the illustrations from this book. The Newtonian equations are the fundamental laws of non-relativistic mechanics. But as we have discussed the equation of motion for various situations, and we come to that conclusion that the vector nature makes them simple to use only in some situation. For example, in describing the motion in the Cartesian coordinates. But in the Lagrangian equation, that represent a reformulation of the Newtonian mechanics that enable us to actually use those description in a general coordinate system, which is not always the Cartesian coordinate. Now, important examples are the polar coordinates in describing motion in the plane, while in spherical and cylindrical coordinate system while describing the motion of objects in 3 dimensions. But the important aspect of the Lagrangian mechanics is that it provides a great power to develop those basic equation that takes the same form in all the coordinate system. So we will see the equation for the Lagrangian mechanics. We'll see the derivation in this lecture. Now, to reach the Lagrangian equation, we'll start with the Newtonian mechanics. So we know that in Newtonian description we start from the second law applied to each of the particles in an n particle system. For example, we have a system of n particles, so in order to describe the motion we need to write the equation of motion, which is just the Newton second law. This is written for the ith particle, so this is not n, this I run from 1 to n. That is, we have n such equations. Now, to get away from the vector description, we need to transform these n equations into a single statement that will be based on this Lagrangian equation about a scalar quantity which is equivalent to all the n equations. Now, to do this, we need to introduce the concept of virtual displacement. Now, this virtual displacement of the system is defined as an arbitrary displacement of each such particle, that is from 1 to n, but with the time frozen. That is, in another word, it is not the physical displacement that could happen in a time, say small time delta t, but rather it is a mathematical displacement which we can carry out conceptually at a frozen instant of time. Now, this equation 1, which are n equations, follow to have this statement. which is based on the same concept, which is nothing but the work done. Now, if we start from equation 1, and then this equation 2 is trivially obvious. Now, what is the significance about this equation 2 is that it is the statement hold for the arbitrary virtual displacement, say this delta Ri for the ith particle. Then all n Newton equations, these all n Newton equation that is represented by this equation 1 must follow. Thus the entire set of Newtonian equations, the all set of Newtonian equation is equivalent to the statement given in this equation 2 is true for each of the instant of time for any choice of the virtual displacement. Now, our aim is here to find out a way to write this description, which is the Newtonian description based in this equation number 1, in a way that is valid for any coordinate system. As I told you in the beginning, that we'll be reaching to such description, the Lagrangian mechanics, where the statement, or we can say the basic equation, will take the same form in all coordinate system. Now, to reach that Lagrangian equation, we need to have some introduction to the generalized coordinate, so that the equation of motion, or we can say the description of motion, is such that it remains the same in all the coordinate system, or we can say take the same form in all the coordinate system. So for that we need to define a generalized coordinate of say 3n numbers, since if a system is having n particle, or we can say we have an n particle system, so for that we require 3n number of ways in which the system can act independently. So a number that qi of t, whose values at any time uniquely specify, we can say, the position or the configuration of all n particle in that system. For example, the 3n components xi, yi, zi of the n 3 vectors r of sub I are one possible choice of generalized coordinate. If you remember, in my last lecture we have discussed the degrees of freedom, or the number of independent ways in which a system of say n particle act. So there we have discussed that if we have one particle system, so for that we required x, y and z coordinate to describe its motion in space, three-dimensional space. So in that way, if we have two particles, so that and they are not connected, that means no constraints are there. Both the particles are free to move in all the three dimensions. So in that regard, we will be having two particles, and for one particle we will be having x1, y1 and z1, and for the second one we will be having x2, y2 and z2. So if we have a two particle system, so the number of independent ways in that situation, x1, y1, z1, x2, y2, z2, so in total there will be 6, the number will be 6. So in this way, if we increase the number of particles in the system so that it reaches n, that means we have a system of n particles such that for one particle we have x1, y1, z1, for the second x2, y2, z2, and say for the n particle we have xn, yn and zn. So in total, if there are n particles for one particle we have 3 configurational space, so that in total we will be having 3n components that will be xi, yi and zi for the ith particle. Similarly, that is for the Cartesian system. The equally acceptable are the 3n numbers, say ri, theta I, and phi I for the spherical polar, describing the position of n particles in spherical polar coordinate. So we want to do then is to transform from the vector coordinates, say if you remember on the previous slide we have shown that in the Newtonian description we have this I runs from 1 to n, so we need to transform this vector coordinates to this j, which is representing the index of this generalized coordinate q. So if we manage to transform these vector coordinates, then we'll be setting the ground for the Lagrangian mechanics, which is based on these generalized coordinate, so that the description will remain the same in all the coordinate system. Now, in doing so, in the mathematical terms, each of the vector r of I can be regarded as a function of the new coordinates q of j. That is, we need to transform these r's to q's. That is, the r runs from 1 to n, and the j, that the index of this q run from 1 to 3n, as I have discussed on the previous slide. So this is the transformation, that is, all these r1, r2 up to rn for a system of n particle, the position vectors can be transformed to a new coordinate which depends upon these q's, where these q1, q2 up to q of 3n. Now, just as we can express these r of I which are given on the left hand side in terms of qj, we assume that it is possible, given that r of I, to go back uniquely to find the q of j. That is, in another word, this transformation of coordinate must be invertible, that is, we can go both ways. Now, this transformation can be clear on the next slide, where we have shown an example of these coordinate. Now, to understand that transformation of that coordinate, that is transforming the position vector, the vectorial form which runs from 1 to n to a new coordinate q of j, where j runs from 1 to 3n, we need to see a simple example, that is, instead of n particle system, let's say we have a 1 particle system whose position vector is described by this r, which is the function of x, y and z in the Cartesian coordinate. If we describe its position in spherical polar coordinate, for example r, theta, phi, we need to use these transformations. So in order to understand the transformation given on the previous slide, if we just understand this transformation for a simple system having 1 particle, and we need to transform these r to, let's say, these are q's. So in order to transform this, we need to have this transformation which is clear to u, that is x is r sine theta cos phi, this y is r sine theta sine phi, and then the z is r cos theta. That is the transformation, the standard transformation from the Cartesian to the spherical polar coordinate. So in the same way, we have written this in a general form, but for a system of n particles. And also, I told you that the transformation are we can say need to be invertible. That is, we need to go both ways, as we have discussed on the previous slide. So thus the three QJs would be Q1 is r, Q2 is theta, and Q3 is phi. That is, these new vectors are the functions of these r, theta, and phi, which are the generalized coordinates. And for any set of values of the QJs, we can calculate the value of r. Likewise, we can find QJ given x, y, and z, as we know that these are the inverse transformation for a system that we have discussed, that is the system is having one particle, and we need to transform the position vector from the Cartesian to the spherical polar. So this is the transformation, and this is the inverse transformation. So on the previous slide, I told you that these transformation need to be invertible. That is, we need to go both ways. Now, to use the generalized coordinate and the transformation that we have discussed, we need to use these transformations in the D'Alembert principle of virtual work, which we have discussed. So we need to transform this delta r to these new coordinates q's. So that can be done. We begin by noting that since r of I are functions of the q of j's, we can use the basic definition of the partial differentiation to express the virtual displacement, which is this delta qi. So using these transformation, we can write this delta r in terms of those new coordinates q of j's based on the partial differential definitions. That is, a small change in r can be expressed or in the transform coordinate for a system of say n particles, so that we have three n number of ways in which a system can act. Now, similar to that delta r, we have this delta qj now, which describe the virtual displacement expressed as changes in the variable q of j. That is, as this delta r represent the change in the vector r. So now this delta qj represent the change in the coordinate q. So this will enable us to transform this D'Alembert principle of virtual work to these new coordinates. So that can be done. Here we have two terms. One is the mi r double dot times delta r minus f of r dot del r, delta r. So first we need to transform this force term over here. So this f dot delta r can be expressed where this I runs from 1 to n. We have a system of n particle, so that if we put instead of this delta r based on this new transformation, so that this summation I 1 to n f of I is the same dot. Instead of this delta r of I, we have now this summation, since we have a system of n particles. So that can be expressed in this way, where we have just interchange the summation over I to j, and that will give us this q, which is this term inside this the parenthesis, so that this is known as the generalized force associated with the generalized coordinate q of j. So this is the second term which we have transformed into that generalized coordinate, expressing the virtual displacement in terms of generalized displacement, so that we have the generalized force form. Similarly, now we need to transform the acceleration term, which is this mi r double dot sigma of r, so that this summation I from 1 to n mi r double dot delta r. So instead of this delta r, we have replaced this the transformed delta r, so that we have this new form. Now, to simplify the inner sum, we have written that in this form, where we have just used the product rule for the derivatives, and since this r of I and this q of j, this r of I and these q of j's varies with time, as I have shown on the previous slide, that they are the functions of time. We can use the chain rule to rewrite the r dot in terms of that new coordinate. So this tells us mathematically that this r dot is the function that depends upon both qj and this q of, say, k separately, and this will tell us that this r dot is a function that depends on both this qj and q dot of k separately. As I told you, that since this q dot of k appears linearly, it is easy to see this that is this change in the r dot with respect to the q dot is nothing but can be expressed. You need to just follow the mathematical step so that it will be easy for you to understand. So using this expression, the second term that I told you that we need to transform, which is the acceleration term, can be now takes this form. If we use this expression in the on the previous slide, which I have shown here in the yellow, so that the acceleration term in the D'Alembert principle takes this form, so that the last step using the equation this one and this one, we can have the total form of the acceleration terms as this one, which can be further solved to put both the terms in the D'Alembert principle. That is, we have two terms. One is the acceleration term, and the second one is the force term. So combining both the terms, using the previous mathematics, we can have the form of the D'Alembert principle given like this. However, this equation must hold for all possible virtual displacement q of j's, as I told you that the transforming equations were from 1 to n, so that now in the generalized coordinate we have from 1 to 3n, so this must hold for all the virtual displacement occur for all the coordinates. Now that is possible only if for each value of j we have this thing, that is this is for the j coordinate, or we can say the j part of that system which independently act from 1 to 3n. Now these equations for j, say as I told you from 1 to 3n, are one form of the Lagrangian equation. Now as I told you, just to tell you that on the previous slide, that T represent the total kinetic energy of the system. So if we want to transform that form of the Lagrangian equation for a conservative system, so we know that F can be described as a gradient of the potential. So we need to relook at the definition of the generalized force as we have discussed on the previous slide. So if we use this thing instead of this F, if we describe it through that potential, so that this will take this form, that is the generalized force can be described through the generalized coordinates q of j, that is we have transformed the r to q's through that q, that is we have on the previous slide we have written q of j as the generalized force, but now using that definition we can transform the form of the generalized force, so that if we use this q of j, the generalized force in the Lagrangian equation which is given on the previous slide, so that it will take this form, that is this q of j is replaced by curly of v, which is v is the potential with respect to qj, and the rest of the equation is the same. Now since the potential energy is a function of the position, we can regard this as a function, this is the function of q1, q2 up to qn, which depends on the q of j but not on the derivative of that thing, that is the generally for conservative system the potentials are position dependent, and they are independent of the velocity. For example, this q that for example represent the first derivative of that coordinate which represent the position vector. So in that way this equation takes a more general form, that is if we take the derivative of this potential, which is scalar potential with respect to the q dot, which is the say the velocity coordinate in the generalized system, so that for a conservative system the Lagrangian equation finally takes this form, that is if instead of writing this t, if we write t minus v here instead of this t, if we write t minus v and here t minus v, so that here the derivative of t of t will be there, the first term, and the derivative of v with respect to q dot is 0, so that we can generally write this expression as instead of the total kinetic energy, we can write the in terms of the Lagrangian function, which is L. Now this L is defined as the Lagrangian and defined as L is equal to T minus V. The important thing is that these are 3n equations. That is, this J is 1, 2, 3. So for a system of n particle, we need to have 3n independent equations, which will take the same form in all the coordinate system. We need to just identify the best way to describe that system through those q's and q dot. So instead of writing this t, we can write this in terms of L, since if we put this L here as t minus v, so the derivative of this v term with respect to q dot is 0, and we'll be left with this form, which is the Lagrangian equation for describing the system of n particles for a conservative system. So after this derivation, we'll be using the Lagrangian equation in various situation, and we'll be describing the motion in the same way as we have done in the case of Newtonian mechanics. In the Lagrangian formalism, we may use any coordinate system. The equation of motion looks the same. The only requirement is that we must express the kinetic energy and the potential energy in terms of this qj and q dot of j, which we have chosen. Now, in practice, the safe way to do this is to first write the kinetic energy and the potential energy in Cartesian coordinate, and then use the transformation that we have discussed on the previous slide to get the t and v in terms of the new coordinate q and q dot, such that each of the coordinate q of j is said to describe a degrees of freedom. As I told you that for a system of n particle, we need to write these 3n equations. So in this way, we will be describing the motion for the for a system describing that will be describing through the Newtonian mechanics. Now the transformation that I told you is given by this. So as I told you, first we need to write that equation, and then we need to transform that in terms of the new coordinate, which is desirable for that, or we can say easy way to describe it. So doing that, we'll be solving some problem over there. So with this, I thank you for your time.